Okay. So the characters of z hat, these can be identified actually. This is so under pointwise multiplication. If you take z hat with pointwise multiplication, that is isomorphic to the circle group, because evaluation of e to the it and e to the is, if you take those two, one maps n to e to the int, another maps n to e to the ins. If you multiply, you get e to the in into t plus s. So it corresponds to e to the it times e to the is. So this z hat is, so these are dual to each other in that sense. The characters here are indexed by z, not only indexed by, the group structure of multiplication is same as z plus. Similarly, characters of z with the group structure of pointwise multiplication is isomorphic to t. Okay, and then we have but there is a slight subtlety compared to the finite case, which is coming from the following fact that here L1 of t, it contains L2 of t, and it is contained. Okay, I'll put a quotation mark here. It's not exactly M of t. So M of t will denote the space of finite Borel measures. Okay, so this is I put a quotation mark because as I mentioned, if you have a positive L1 function, it can be thought of as the density of a measure. But general L1 functions, it's not exactly cannot be identified with a measure. It can be identified with a complex measure, but for me, measures means positive measures. So that's why I just write it in a quotation mark. Anyway, if you can do something for positive L1 functions, you can usually extend it to all L1 functions. So there will be no, so in that sense, it's okay. But here it goes in the other way. So here, if you look at M of Z, L1 of Z and L2 of Z, here the inclusion goes this way. L1 of Z is like this, and M of Z is actually sort of equal. Again in quotation marks, because only positive L1 functions can be, because any measure here can be written as a superposition of delta measures, right? So this is the case. So because of that, there is a slight difference in the way we have to define Fourier transform. So what is natural is, so in both cases, here for f in L1 of t, we define f hat of n to be integral over t f of t e to the minus int dt over 2 pi. So this is well defined, and here also it is the natural domain for defining the Fourier transform is this L1 of z. We can define g hat of, now we define it as g hat of e to the it or g hat of t, whichever you want to say, is sum over n g of n e to the minus int. Okay, this is like it's formally it looks like inner product of g with this ev e to the it. Here it looks like formally like f inner product with that, but if this is not inner product, it's a pairing. Okay, so because these are bounded, characters are bounded, you can integrate them against L1 function. So this is the natural definition. But on the left side, what happens is because of this inclusion, okay, or let me also define for mu in M of t, you can similarly define mu hat of n as here, this defines it also for L2 functions. Because L2 is contained in L1. Here, however, you have to indirectly extend it to L2. I say extend, it's not strictly extend. What you do, extend from L1 intersection L2 to L2. This we did last time. If you consider L1 intersection L2, there the Fourier transform defines an isometry, and then you can extend it to L2 of Z, right? So this is what we did. last time. So this is the summary, and then what we have is something that Planchaga, etc. we can write. So the L2 theory becomes neat. So let's write it for if f is in L2 of t, then f hat is in L2 of z, because it's just the Fourier coefficients, and f is in L2 of t, the sum over n in z, f hat of n e to the I n t. So this I should write f of t. In L2 sense, it is this, meaning the partial sums converge in L2. So, and what we can say, so because of all this, so you have to go through this indirect extension. This can be written as equivalently. So this is same as the Fourier transform of f hat. Okay, so f hat is in L2 of z. So let me just write like this: the Fourier transform on z applied to Fourier transform on t. Let me just write f hat here. Fourier transform of z applied to f hat, but evaluated not at t but at minus t. If you see here, it is with e to the minus I n t. Here it is with plus, so that's why this is like this. So in other words, f you can recover by applying the Fourier transform back, but what you get is not exactly f, but f flipped over by minus t. And you can go the other way also. So you can start with g L2 of z, then g hat belongs to L2 of t. Okay, so you have to check these things. Okay, because the definition was a bit indirect, you have to check that it is actually L2 function, because it's defined by some limits, right? You define it on L1 intersection L2, then it's okay. G hat is defined by this formula. But if it's not in L1, you have to take L1 intersection L2 and then extend to that. So there is a limiting procedure. So one has to check that G hat is in L2, and if you apply the Fourier transform on T to G hat of n, you will get G of minus n. So you can recover. So in that sense, the Fourier transform, this is the Fourier inversion that I am writing. So I won't give more detailed proofs. I will leave you to check this. More or less it has been done. You just have to go through this indirect definition of the Fourier transform. That's all. So this is Fourier inversion. So to put it again, if you apply Fourier transform of z, Fourier transform of t to f of t, you get f of minus t. Okay, for f in L2 of t. And the other way. So Fourier transform of t composed with Fourier transform of z applied to g of n is g of minus n for g in L2 of z. So this is the L2 theory. And as a corollary, we also get ft L2 of t to L2 of z is a surjective isometry. So in particular, f L2 of t will be f hat L2 of z. And fz similarly goes in the other direction. It is from L2 of z to L2 of t is an isometry, and that means that g, if you take in L2 of z, it's the same as its Fourier transform in L2 of t. So that's a kind of summary plus a little more that I have said. all this is left as for you to think about. It comes from everything I have said so far. Any questions, comments at this point?
This may be a stupid question,
No.
you mentioned that L1 of t is a superset of L2 of t.
Yes.
And then, in other words, why are we working hard to get an L2 theory? Shouldn't an L1 theory imply an L2 theory? Sorry, this may just reflect my
No, this is no. That's why this side it is easy. In fact, if you go back without if you don't care about all the superstructure of dual group and etc. When once we proved Feyer's theorem, okay, once we proved Feyer's theorem, then it was very easy for f in L2 of t. So we proved Feyer's theorem, which was that these ENs form an orthonormal basis. So for L2 functions, if I define f hat n to be this coefficient, it is just the expansion in the basis, and you immediately get all this Plancherel and this. Right? So it's immediate. But so you're perfectly right in saying that. But why I digress from here is that it looks a bit different from the inversion formula in the finite case, where one side you have integral, another side you have sum, and so on. So what is the conceptual framework here? So that's what I went to. So that's where this business comes in. But once you want to make this business precise, you have to define Fourier transform on integers. But once you go to Fourier transform on integers, the inclusion goes the other way, and L1 theory does not immediately give you an L2 theory.
I see. Okay.
So there you have to do this little trick of first restrict to L1. You define L1, you can naturally define Fourier transform. On L1 intersection L2, you check the Plancherel formula, basically that on L1 intersection L2, the Fourier transform preserves the L2 norm. This I did last time. You said you couldn't connect. So
yeah,
I did
look at the recording. Thanks.
Yeah. So on L1 intersection L2, you have this isometry, and then by general abstract nonsense, you can extend the Fourier transform to L2 functions. And it becomes an isometry on L2Z into L2T. That's the point.
I see. Okay, thank you.
Yeah, so this is actually a kind of one of the reasons is that this is a general feature we'll see when I say a bit about locally compact abelian groups. So even with real line, it is that
one more small question. You mentioned that right thing looks like a inner product, but it is not.
Right.
Somewhere slightly further up.
This one, these things, this when L1, this looks like F inner product with En, but it's not an inner product. L1 has no inner product. The point is, it's an L1 function being integrated against an L infinity function.
Oh, I see. Okay.
Here also, it's an L1 function being integrated, summed against an L infinity function. Because characters are bounded, you can naturally define L1 functions. You can define Fourier transform.
I see. Understood. Thank you.
Any other questions, comments? Okay, if not, now I go to Fourier transforms on measures. So let me go. So this finishes. Go ahead.
What is that two pointer notation?
Which one?
There are two arrows that you have put from L2 to T.
Oh, this is surjective. This bar here, it means injective. Well, isometry is always injective. This is also surjective. See, isometry in finite dimensional spaces is always a surjective map, but here it need not be. What we showed was f hat L2 norm is same as f L2 norm. So, but we don't know that everything in L2Z occurs as this. Okay, it's kind of easy to see, but I just emphasize that this is a surjective, in fact. So this is on to L2 of Z and this is on to L2 of T. Okay.
Okay, thank you.
Yeah. So now the question is, so we have showed this, but now a bunch of questions remain. So I'll go to Fourier transforms of measures and L1 if you want. I'll also put L1 here. So let's look at L1 of T or M of T. So let's now look at M of T. M of T. So let's say So we have the Fourier transform into functions on Z. How? So you send mu to mu hat, which is defined as mu hat of n equal to e to the minus int d mu of t over the circle. So this is how we define this. So various questions are here. So is this injective? So questions. Is this injective? Meaning, can we recover mu from mu hat? What is an inversion formula? So is there an inversion formula? Second question, what is the range? In other words, what functions arise as mu hat? What functions on integers are Fourier transforms of measures? All this was clean when it was L2. L2 to L2 there is a nice correspondence. L2 functions on T and L2 functions on Z are in one-to-one correspondence by this Fourier transform. And even the inverse we understand very well. But here on space of measures, is it even injective? Can we recover? If so, how? And what are the functions which arise here? And similar questions for and third question is, are there some properties of mu in terms of mu hat? Are there properties of mu which can be written in terms of mu hat and vice versa? Okay, so these are questions one can ask, and similar questions for L1 one can ask. So the Fourier transform from L1 of t to functions on Z. C to the Z means functions on Z. Okay, so one can ask these questions and we will answer it more or less. Okay, so the answer is yeah. So we'll stick to measures and answer this. These are nice. So
I just had one thing to ask. Would it be here we're working with measures on T, right?
yes.
Would it be more natural to work with sign measures rather than just measures because that allows you for
True,
take.
yes. So I mentioned this last time. Then it would even contain L1. That would be the nice thing about it. On the other hand, everyone does not end up seeing signed measures in measure theory class. I mean, it depends. So it just is a little bit of unfamiliar language for no great advantage because every signed measure is actually mu1 minus mu2, where mu1 and mu2 are positive measures. And in fact, I would like to work with complex measures because everything I work with complex values. So complex measure is actually mu1 minus mu1 minus mu2 plus I mu3 minus I mu4. Where mu1, mu2, mu3, mu4 are positive measures. So this is called the Jordan decomposition of measures. So one has to invoke these things, but there is no great advantage. I mean, so it's just I thought we'll stick to finite positive measures.
Right. So like everything follows almost just directly from Jordan decomposition, so you don't need to.
Right, exactly. To take that, if you know it, it's for people who don't know it, just makes it unfamiliar language and confusing. So for those who know it, it is very easy once you have this to transfer whatever you want to the other side.
Right.
Okay, and also there are a couple of things here that are specific to positive measures, which I will come to. Okay, so there is a little bit of noise here, some constructions. Yeah. Okay. Any other questions? Okay, so first let me do the recovery theorem. So theorem 1 will be mu to mu hat is injective. In fact, we can recover mu from, so this is m of t to, at the moment it is just functions on, I don't know what is the range. So it is injective means, so can recover mu from mu hat. Why? I will write the formula later here. Okay, I will write the formula which will follow from the proof. So that will be one of the things that we will do. Maybe I just do the proof of this. Let's do theorem proof, then it will be okay. Okay. So before going to the proof, so how will we prove that it is injective? The idea will be to approximate. We understand it well for good functions, so we will have to do it for measures. So what I want to define, maybe I on the side I define convolution. Okay. So okay, here I need space for this. Maybe before the proof, I just recall convolution, which I have defined for functions, not for measures. So if mu and nu are measures on T, you define mu star nu as the function which to a Boyle set A, it gives the measure so you translate A by this T. Okay, A minus T. I'll switch between multiplicative and additive notation. As I said, I don't think there will be any confusion due to that. Here I'm thinking of T as 0 to 2 pi with modulo 2 pi addition. Okay, so you translate A by T and then integrate with respect to nu. Okay, so this is actually similar to what we have done before. If okay, so if mu has a density, let's say, then this thing becomes f of, okay, then yeah, so then okay, let me just say it because I don't want to spend time on this. Then mu star nu has density given by, sorry, let me move to a slightly less is it do you hear the noise or is it just me?
You can hear it sometimes, not too.
It's not too problematic though.
Okay, so then let me just continue here. So has density, which is I'll denote f star nu. The same notation is being used again. F star nu of t will be integral over t f of t minus s d nu of s. But maybe with a 2 pi. Because here I have defined like this. Okay. Yeah. So if both mu and nu have density, then this becomes, we can write it further as integral over t f of t minus s, and this has density g, so it is g of s ds over 2 pi, but there is an extra 1 by 2 pi. Okay, so this is not exactly consistent with the definition I gave before, so I don't know what I should do. Should I put a 2 pi 1 over 2 pi in this definition? No, that would be not a good idea. If mu and nu are probability measures, I would like this to be a probability measure. Let it be like this. So it's slight difference from the earlier definition. This is from my earlier definition. This is f star g of t, but my earlier definition had only 1 over 2 pi. Well, this is what I called f star g. Okay, but okay, let's not worry about these things. So the convolution is something useful. So this one interpretation which you may find it easier to understand is in probability terms. If e to the ix has distribution mu, that's a random variable taking values on the circle. E to the iy has distribution nu and xy independent. then this one is nothing but mu star nu is the distribution of e to the ix into e to the iy, which is e to the I into x plus 1. That's what it is. Okay, so it may be a useful way to think about this convolution of measures. It's the distribution of the product or the sum. If you are working in the exponent, it's the sum. If it's the e to the ix, it's the product. From that, it is one simple point, which is something you can do as exercise maybe, is mu star nu hat is the product mu hat into nu hat. Okay? Fourier transform of the convolution is the product of the Fourier transforms. Anyway, so convolution has many uses. We have seen it before in Feyer's theorem. We did convolution, right? So what we did was we had a continuous function. So if you remember Feyer's theorem proof, we have a continuous function. We took this sigma nf, which was actually f convolved with kn, and because kn was an approximate identity, that was approaching f, and that was how we proved Feyer's theorem. So that's basically the way we are going to use it. So now let me prove the theorem that mu can be recovered from mu hat. Okay, so let me prove that theorem. So mu is directly hard to work with. We approximate it with nice enough things. So what we do is, so consider, let Kn be the Fejer kernel, and you consider mu star Kn. Okay, mu star Kn is basically the measure with density. I'm putting measure here and this here because Kn, I mean, so this is actually, if you want, Kn of theta d theta over 2 pi is a measure, right? It's the mu convolved with that we are talking about. So this is the measure with, like here, if one of them has density, this has density Kn of t minus s d mu of s. I think I have to put it 2 pi or no, maybe no, it is with respect to, okay, just give me a moment. I have to just see something, 1 second. Okay, so this is there 2 pi or not? Kn, yeah. So if this is the density, then yeah. So this is the yeah. What is the density? It is this f of Kn of t minus s d mu of s over 2 pi. Okay, that is the density. Actually, I don't know. Maybe there is no 2 pi here, right? Am I making a mistake? Actually, sorry. When d mu of t is f of t dt over 2 pi, then maybe there is no 2 pi here actually. Maybe I introduced an extra 2 pi. So it depends on what we are expressing density with respect to. Okay. So if I don't put, so with respect to dt over 2 pi, always with respect to normalized Lebesgue measure, then I think I don't need to put this, right? So then it's okay. So I thought there was an extra 2 pi here, but okay, this is actually agreeing with the original definition. Okay, sorry. So I had an extra 2 pi here. Anyway, so mu star Kn is a measure with this density, right? So let's call this something. Let's give it a name. So let's give it a name, which is, I don't know what I give, Fn of t. Okay, so Fn of t. So what is the Fejer kernel? So Fejer kernel, there are different formulas we had. I'm going to use something about Fejer kernel, but we'll write a formula which I did not write explicitly. So let me just recall. Kn of u, if you remember, it is the sum of the Dirichlet kernels. Okay, and divided by n plus 1. Okay, into 1 by n plus 1. But Dirichlet kernel itself is the sum from minus j to j of the complex exponentials. So you interchange the sums minus n to n, you get ek of u, but ek of u comes for all j bigger than k, bigger than or equal to k. So that will be n minus n plus 1 minus mod k divided by n plus 1. Because what it comes for is k, when j is bigger than or equal to k, you get. So j equals k up to n, that is n plus 1 minus mod k of them. So many times it comes. So fn of t we can write as, so this is a different formula from the ones I wrote. It's just a useful way to write it. Okay, this is another useful way to write it. So if you write that and then you integrate against mu, what do we get? Okay, so if we integrate against that, you get, so this n plus 1 minus, so k goes from minus n to plus n. And this n plus 1 minus mod k over n plus 1, let's write it as 1 minus mod k over n plus 1. Okay, k goes from minus n to n. And then what it comes with is ek of t minus s d mu of s. So remember, ek of, what will that be? You can pull out ek of t out, and what you are left with is mu hat of k. Because ek of minus s is e to the minus iks d mu of s. That's the Fourier transform of mu. So here you get mu hat of k times ek of t, which is e to the ik t. Okay, so this is what fn of t is. Now the proof is more or less there actually. So in short, the proof is this: mu star kn. So earlier we saw that if you take a continuous function g and convolve with kn, then it approaches g in the uniform sense. Okay. Now here we are not convolving with a continuous function but with a measure. Nevertheless, because kns are this approximate identity which are concentrating near the 0, the point is, for as n goes to infinity, we can recover mu from mu star kn. So statement 1 will be, now two things. Claim is mu star kn. Okay, or maybe I say it in words. I'll state the precise thing in writing. So mu star kn will approach mu in whatever sense. Okay, so we'll get mu as a limit of mu star kn. Okay, in some sense. But mu star kn is entirely defined by fn, and fn is entirely expressed in terms of mu hat. So this side is entirely determined by the Fourier transform, and taking limits of this, you should get mu. So that means mu can be recovered from mu hat. That's all the proof is actually. Okay, so now let me say in what sense it actually is. So we'll actually get a recovery formula also. So let's write what is the sense in which it happens. So claim is, fix any interval arc, let's say e to the I alpha, e to the I beta, with 0 less than equal to alpha less than beta less than 2 pi. So I'm just fixing some arc like this. Okay, the claim is, if you look at mu star kn, that's a measure, right? So I will write I. Okay, mu star kn is a measure whose measure of I. What happens to this as n goes to infinity? This converges to mu of, okay, I will abuse notation and write alpha beta, which means the open interval here, plus half of the measure at the endpoints. If there is some atom at the endpoints, if there is no atom, then this is 0. Okay, so as n goes to infinity. So it is in this sense that mu star kn approaches mu. If you take any arc, you will get the measure of the arc, open arc, plus half of the measure at the two endpoints. This is the claim. But what? Okay, so why is that true? Once you admit the claim, you are seeing that. Okay, so you get this. Okay, maybe let's finish the claim and then what should I do? Assuming the claim, let's assume the claim and assuming the claim. We can recover mu from mu star kn, n greater than equal to 1 via limit. Because for any, in fact, how? For any continuity points, alpha, beta, not atoms of mu. Okay, what I mean is e to the I alpha, e to the I beta are not atoms of mu. We see that mu of alpha beta is limit n going to infinity mu star kn of I alpha beta, which is, so you get this. And if atoms, there are only countably many, if you know it for all arcs, and this is sufficient to recover so there are only countably many atoms. If you know it at all other points, you can recover because of, there are many ways you can think about it, but I will leave it for you to think about. So if you know this for all alpha beta, which are continuity points, that's enough to recover mu. Okay, so this we get. And then this will be, but what is mu star kn of I? It is just mu star kn of I is just the integral. What is this? So this is limit as n goes to infinity of integral from alpha to beta, this mu star kn of this density fn of dt over 2 pi. And that is nothing but fn is given by this kn of t minus s, which you can write here. Okay, so let's write this fn like this. So this is the limit as n goes to infinity of sum over k equals minus n to plus n. I just put the integral here, 1 minus mod k over n plus 1 mu hat of k. And then I just integrate this e to the ikt over alpha to beta. What happens when I integrate e to the ikt over alpha to beta? I just get e to the ik beta minus e to the ik alpha over ik. But there is also a 2 pi. So you get this. Not particularly pleasant maybe, but you see the right hand side is entirely in terms of mu hat. Hence, you can recover from mu hat. So this is not a particularly beautiful looking inversion formula, but it is enough to show the injectivity. Okay. Any questions here? Modulo the claim. The claim I have to yet show, but other than that, this is shows the recovery. Any questions? Okay. If not, let me just, we need to still prove the claim. So let me just do that. So this is actually a nice formula recovery, and so this proof also I wanted to give because this is the way you have to work. I mean, you have to approximate measures or in analysis generally. L2, L1, these functions may be not so nice to directly work with. You have to convolve to get some nice things and then you work with them and take limits. That's the usual way. So now let's prove that claim. Mu star kn of I converges to this. So let's look at mu star kn of I. I will not use this formula, but it's the same. I mean, I have written it in certain way here in the inversion formula, but here we will use the properties of Kn we have seen before. Namely, so this is the integral over, this is correct, right? Fn of t dt over 2 pi, that's the density. But now we will write it in a slightly different way. Fn of t we will write in this form. Kn of t minus s d mu of s. So this is the integral over the circle of Kn of d minus s d mu of s and then dt over 2 pi, because that is the, this is I, that is t. Okay. So now we interchange integral. Everything is okay because this is a bounded function and positive and everything. Kn is positive, so we can interchange the integrals. Integral over t, integral over I, Kn of t minus s dt over 2 pi, and then we do d mu of s. Okay, so let's look at the inner integral. What is this actually? Kn of t minus s dt over 2 pi. Maybe I just very quickly go back and recall for you that Kn is an approximate identity. Kn has this property that it is looks like this. If I flatten the circle, it has this peak at 0 and it's a probability density that concentrates near 0. Okay, in the sense that if you take any delta minus delta delta, then in probability outside will go to 0. So Kn of t minus s is the same thing shifted to s. That's all, right? So what is Kn of t minus s? So let me just write a picture here. So let's say alpha is here and beta is here. Okay. So if s is here, then Kn of t minus s is something that is like this. Okay. So the point is, if s is in the interior of alpha beta, okay, if s is then the integral over I is this alpha to beta, right, of Kn of t minus s dt over 2 pi, that converges to 1, because any positive interval around s, the integral will go to 1. Everything outside goes to 0. So if s is an interior point, then it does contain a neighborhood around s. The interval contains a neighborhood around s, and so the probability of that converges to 1 as n goes to infinity. Okay, that's okay. And if s is outside the closed interval, so suppose I just erase this and draw a picture again. For the same reason, if S is an interior point outside, then its probability concentrates around this. So in the complement, it puts most of the probability. So the integral on the inside, this part is separated from S. There, this will converge to 0 because nothing is there. Okay. The delicate part is when S is right on the boundary. So if this beta is equal to S, let's say this is S, then the probability concentrates like this, but what happens when you take the integral Kn of t minus s dt over 2 pi, that is actually at all, it is kind of, it converges to half. Because of the symmetry, there is half to the left and half to the right, and only the part which is falling inside the I matters. Okay, so it's not exactly equal to half at all times because this alpha is also a barrier, but ultimately that will not cause any trouble because that is far away from beta. So most of the probability will be in a neighborhood of beta, but it's symmetrically placed around. So only half of it comes. So that's why you get this. So this inner function, so this function, so if we call this for the moment, let's call it phi n of s. So phi n of S converges to 1 if S is in alpha beta, half if S is alpha or beta, and 0 if S does not belong to the closed interval alpha beta. Also, phi n is always less than equal to 1 because this is Kn is a probability density. If you integrate, you get less than equal to 1. So by dominated convergence theorem, this will converge to integral of alpha beta plus half indicator of alpha beta, half indicator of the boundary points d mu of S. Right? Dominated convergence theorem tells you that this converges to this. This is the thing written in this form, which is exactly mu of the open interval plus half of the mu of the endpoints. Okay, so that completes the proof. Any questions here? Okay, so you may have seen similar argument probably on the real line if you have ever taken a probability theory course and so on. So you may have seen this stuff. Okay, so that is there. So we have an inversion formula also. We have proved the injectivity of Fourier transform. We also have a recovery formula which is not particularly good, but there are cases where it is good, and that indicates some features of Fourier transform. But before that, if there are no questions, then I continue. Okay, so from this you also deduce, so I'll leave this as exercise. Fourier transform is injective on L1 of t. So this is linked to the question Aditya was asking that, well, okay, in a way, can you deduce it from this? There are two ways to think. Can I deduce it from theorem 1 or you imitate the proof of theorem 1? Both are possibilities, both can be done. But if you are trying to deduce it from theorem 1, you have to pay attention that every L1 function is not density of a positive measure, whereas the proof I gave is for positive measures. That's all. Okay. So I leave that. Let me go to something else. So the recovery formula. So let's write a corollary, which is, I'll write the corollary and then tell some things about the Fourier transform. It's a very important property of Fourier transform. I mean that it will be indicated here. Suppose mu is a measure, finite Borel measure on T, and suppose mu hat is a summable thing, L1 of Z. There is no guarantee of that. Then mu has a density in fact, I'll write the formula for the density. It is mu hat check of minus t. What I mean by that is, it is sum over n in z. This check case, you may remember I had introduced it in finite abelian case. Oh, sorry. No. If I write check, then there is no minus t. So let me write mu hat of minus t. So one has to be slightly careful. The first hat is in the Fourier transform on the circle group. The second hat is Fourier transform of on Z. So what it means is mu hat of n e to the int. Okay, with respect to normalized Lebesgue measure, actually dt over 2 pi. So this is what is the density of the mu. So if mu hat is summable, then this is absolutely summable, right? So this makes sense for each t, and this is actually the density. It is also a continuous function, but okay, let's not worry about that. It's the density. Because this is absolutely summable, this is actually fine. So how is that following from here? It's just that this formula we have to, okay, so this, but what is the gist of the corollary? So the proof is not hard. We have seen mu of alpha beta plus half mu at the end points is equal to a limit as n goes to infinity of k equals minus n up to n mu hat of k e to the I k t, and then there is also 1 minus mod k over n plus 1. Yeah, we saw this, right? I mean, so this is what is the recovery formula, which is here. Oh, sorry. Oh, sorry. There is no e to the I k. Sorry. There is no e to the I k t. It is that other thing. It is times e to the I k beta minus e to the I k alpha over 2 pi I k. Actually, you should have objected a little bit here. So this is actually not correct. I mean, so this is a bit meaningless. So the k equal to 0 term to be treated separately. So when k is 0, you don't integrate e to the I k beta I k t like this, right? I mean, the 0 in the denominator is confusing. So this k equal to 0 term should be interpreted as mu hat of 0 times this is 1. And then here you just get beta minus alpha over 2 pi. Okay, as long as you take it in that sense, this is okay. Actually, yeah, that e to the I k t, when k is 0, you have to integrate and it gives you beta minus alpha over 2 pi. So with that, let's keep that convention. So with here also k equal to 0 means this we treat as beta minus alpha over 2 pi. Okay, in the limiting sense as k goes to 0. So that's how we think of it. So this we know. But now mu hat is summable. So mu hat is summable. This is bounded by 1. This is also bounded by 1. Okay, so in fact, e to the I k beta minus e to the I k alpha is always e to the I k some number gamma k times beta minus alpha, and then there is a I k, right? The derivative for some gamma k which belongs to the interior of alpha beta, right? So mean value property or whatever that is called, mean value theorem. The difference is the derivative at an interior point times the difference. Because of that, the summand is mu hat of k 1 minus mod k over n plus 1 times I cancel. So I get beta minus alpha over 2 pi times e to the I k gamma k, which is bounded in absolute value by mod mu hat of k times beta minus alpha over 2 pi. Okay, so that's what you get. So because of that, you can apply, you can take this limit. I mean, so this is which is summable. Hence, by dct, what we get is mu alpha beta plus half mu of the endpoints will give me exactly. I just take the limit as n goes to infinity. What happens as n goes to infinity? This goes to 0. That's all that happens. Is actually mu hat of k e to the I k beta minus e to the I k alpha over 2 pi I k over k in integers. Okay, that is one point. And also, and the right hand side is bounded by beta minus alpha over 2 pi into the L1 norm of mu hat. Okay, so you see that any interval even if you take the endpoints, it's half of the endpoints. The measure is bounded by the length of the interval times something. So when the length of the interval goes to 0, this goes to 0, which shows that there can't be any atoms actually. Not only there are no atoms, this shows that there is absolute continuity actually. So maybe I just leave it at the moment. So this implies that mu has
it's 1 o'clock.
Density, which is actually this. This is actually, okay, not this. It's the derivative of that. It's the derivative of that. This was the integral. So this is just the derivative in, if you fix alpha and differentiate with respect to beta. So it is k in z, mu hat of k, e to the I k t, and this is bounded by, okay, yeah, that's all. Yeah, that is the density. So this is the point. So this completes the proof that if mu, if an addition, so you have a slightly better inversion formula as a point, that if mu is a measure with whose Fourier transform is in addition assumed to be L1, then it's a slightly better inversion formula. Instead of writing a limit, we have written a infinite sum. Not only that, it has but one feature of this, important feature of this, I'll remark more on this later, is that, so the corollary shows dk of mu hat implies smoothness of mu. See, we assume that mu hat decays fast enough so that it is L1. Then mu has a density. In that sense, it is a smooth measure. Okay, it's a somewhat smooth. It has a density. If you assume further decay of mu hat, you can deduce that these densities are C1, C2, and so on. That also can be done. So, but this is something that you should always remember, that this is the way. The other way is also going to be true. Smoothness of mu will imply decay of mu hat. Okay. So this one I will do it next time. So this is a lemma that I will prove next time, that if mu in M of t has density, then mu hat of n goes to 0 as mod n goes to infinity. So this you should remember in the qualitative way. Decay of mu hat implies smoothness of mu. Smoothness of mu implies decay of mu hat. Why? I will explain next time in electrical engineers language, which is very intuitive. Okay. So this is something to keep in mind, but the theorems don't go like that. I mean, it's not exactly converse. So mu hat, if we assume is in L1, then mu will have a density. But if you just assume mu has a density, you don't get mu hat is in L1. You just get mu hat goes to 0. Okay. So it's always a little bit of loss that way. If you go and come back, it's not exact converses, but like this. Similarly, if you assume mu has C1 density, then you can get further decay of mu hat and all that. Maybe I will put some of them as exercises, but okay, I will stop here. Any questions, comments?